we have 7 problems to complete by next Tuesday. So first 3 problems on Lyapunov exponent. In fact, they are very easy. It's again, I took them from exam papers. And these are usually, this is a sub-problem from problem number 2. So problem number 2 has 2 sub-problems. One sub-problem is on calculating Lyapunov exponent and making conclusions on what was calculated. And second sub-part of problem number 2 is about finding fractal dimensions, analyzing fractals and finding their dimension. So this is exactly what happens. As you can see now, so I had to deliver quite a lot to prepare you for, let's say, set work number 2, for homework number 2. But for homework number 3, it's 1 week material. And this is pretty much will be like this. I will somewhere slow down, but when it comes to what is useful for these homeworks, it's usually like 3-4 lectures, not more. So these 3 first problems, eventually they all are discussed in lecture notes part 2 at the end. If I can find it. Can you see my screen? You see my screen. So I go to lecture notes part 1. Here. This example number 5. Can you see it? Can you read it? So this, I didn't discuss it in my lecture, but it is basically, if you understand what is in there in example 5, you should be able to complete all 3 problems in your set work. We had in example number 5 in lecture notes part 2. Now, so this, if we want to plot it, it will be something like this. Let's plot something like, for example, b is 0 and a is more than 1. So it will be something like this. 1, 1. Slope is given by a. If a is more than 1, so this is diagonal line. So it will be
yeah, we did.
Good. Now again, x n plus 1 equals axn plus b mod 1. So this is all 3 first problems like this. In the first problem, we can look at it. So in the first problem, a equals to 1 and b replaced by a. Yeah, can you see it? Just look at problem number 1 in set work 3. Yeah, so in problem number 1, set work 3, a is 1 and b is replaced by a. So it's just different notation. In set work, in problem 2, a is 0, but b is 0. And in problem 3, now we have I and double I. In I, a is 3 and b is 0. And in double I, a is 1 and b is pi over 4. Right? Did I convince you that all of them come here? Good. Now I will get back to plotting. xn plus 1. Now you can, well, let me consider this case, first case, xn plus 1. So this is problem number 1. equals to x plus a. So this is a, and so slope is 1, so it will be something like this. So this is our diagonal line. What we can say. So what we can say that there are no fixed points, for example, here. And if there are no fixed points, then what it will be? So there is no convergence to anything, and eventually it will be no divergence to anything. Now let's consider, so in xn plus 1, x plus a. So here we can consider two cases. A is rational and a is irrational. So if a is rational, everything is relatively easy. If a is rational, then a can be represented by a ratio of two integers, n and m integers. And what it means? It means, by the way, I forgot here to put one. Consider, so let's say we have x naught. We started with x naught. X1 will be x naught plus n over m. And what I am interested in xm. Xm will be equal to, so this is mod 1, keep forgetting it. So it will be equal to x naught plus this guy m times, because every next time we add this term. So now when we can get to xm, we added this term m times, which should be equal to x naught plus n. And if we consider mod 1, n disappears, because n is integer and mod 1 means take out all integers. Therefore, what we get? We started with x naught, and after n iterations, we got again x naught. What we got? We got periodic solution. So this is first conclusion you do. Yeah, so at least in this map. If a is rational, then you will have a periodic solution. And if it's irrational, you can't get it like periodic. So it will be not periodic because you can't represent a as a ratio of two integers because if it's irrational, and therefore you never will get x naught. It is one point. And second point, if we talk about Lyapunov exponent here is eventually 0 because you see, so maybe clear. I don't have here any other, so I clear. I will clear. So what we considered xn plus 1 equals to x plus a. And here we concluded that if a rational, then the dynamic is periodic. Also, orbit is periodic. And if a is irrational, it is not periodic. On the other hand, so I forgot again mod 1. On the other hand, it's bounded. And these kind of solutions which are not periodic, bounded, and it's not chaotic either. Not chaotic. So not chaotic. Now, bounded, we understand why it's bounded because x n always will be between 0 and 1. It's a reminder after you take out all integers. So this will be this is a number between 0 and 1, always for any n, it is bounded. Not chaotic, because if you check Lyapunov exponent, you remember Lyapunov exponent was average value, so logarithm of f prime at xi, whatever it is, average. But also f prime here of x equals to 1, because f of x is x plus a and derivative is 1. And therefore, it will be logarithm of 1, it is 0. So 0, generally, it's again, so when Lyapunov exponent is 0, it's not conclusive whether you have the chaos or not, but so if it would be quadratic or cubic with Lyapunov exponent 0, then you would need to make further consideration. But for linear map like this, so this Lyapunov exponent 0 means you don't have chaos, and therefore we say it's not chaotic. And if it's not periodic, bounded and not chaotic, there is special name for this. It's called quasi-periodic. Quasi-periodic. It is, this term comes from well, it comes from another consideration. It's like motion on Tor. So somehow this quasi-periodicity and periodicity is related to motion of point on the torus. So you can imagine it. It is, well, you don't need to remember this. It's not related to your exam. But you can consider a point which moves on the torus. And if it moves on the torus, makes loop after loop, it has basically two periods. One period along long axis of torus, and second along circles which it makes on the surface. So there are two periods, and if these two periods can be represented like if their ratio, let's put it like, if their ratio is rational, then you will have periodic solutions. It will be repeated eventually. And if it's not rational, then it is not periodic. On the other hand, it's always on the Tor. And here we could put even more. We could say that since Lyapunov exponent is 0, derivative is 1, we can say if we have two orbits which started very close to each other, distance between them will be always the same. And now what you can say, so this if distance is the same, well, it's not very good argument maybe. Anyway, so this quasi-periodicity, usually people refer to this motion to torus, but I don't consider it here, because if I would like to make this, to translate it to motion of particle or point in torus, then it would be a long story and it would not fit into our syllabus. But what is good, you can remember it's quasi-periodic. You can, so very weak argument is like this. If A is irrational, you can approximate it by a rational number. And as soon as you approximate by a rational number, it will be periodic. And so any approximation makes it periodic, but in fact it's not. And that's why it's called quasi-periodic. Let's put it like this. Yeah, is it convincing? Okay, so this was about problem number 1. Now let's consider problem number 2. So in problem number 2, we have xn plus 1 equals axn mod 1. So now it is different. Now we have a slope is defined by parameter, but it always starts at 0. So if a is more than 1, let's put it like this. If a is more than 1, it will be something like this. Okay, let's put it like this. So this is 0, 1. Some numbers same should be the same number. So here we have a more than 1. And if we draw a diagonal line, we will have some fixed points. Now we have fixed points. We can have fixed points, not necessarily. And if a is less than 1, it will be shallow. This is our diagonal line. So now let's again, so we have this fixed point always at 0. And here we can have extra fixed points, but here we will never have an extra fixed point. So this is two cases, a more than 1 and a is less than 1. And a equal to 1 is nightmare in a sense, because this is a equal to 1 and it will be same, diagonal line is the same. I don't know how to change color here. Here. So okay, so our function coincides with diagonal line. So everywhere is the same. Xn, xn plus 1. Xn, xn plus 1. Here you have infinitely many. So all values of x, any x is fixed point. So okay, all x in this domain are fixed points. Good. Now, if we look at Lyapunov exponent, so since f prime here, f prime equals to a more than 1, therefore lambda, which is logarithm of f prime, logarithm of f prime will be negative. And here lambda, no, here will be positive because it's logarithm of number which is more than 1. And here lambda will be negative. So here, and so here we can't have no chaos, obviously. In fact, this is stable. It's so this point is, you can check it, it will be stable. X equal to 0 is stable fixed point. And here, all fixed points are stable because at all fixed points, derivative is more than 1. And here we have chaos because Lyapunov exponent is positive. And this is difficult case. It is stable, no unstable. And now what we're supposed to do in problem number 2, find Lyapunov exponent. I already found. And when a equals to 2, sketch the function f and describe the evolution of the system. So you just find x naught for this x. Well, x naught is given. Find x1, find x2, find x3, and then on what you calculate, get to like first 5 or 6, and then you can see what is going on there. Good. So this was about problem number 2. problem number 3. In problem number 3, we have I. Yeah, but well, I don't want to tell you because you see, this I is like problem number 2, where A equals to 3. And double I is like problem number 1 when A equals to pi over 4. So this is, in fact, I already discussed both these cases. What I would rather do, I would rather go to this example number 5 at the end of lecture notes part 1. Xn plus 1 equals Axn plus b. So this is in mod 1, between 0 and 1, everything. Now, so what I said there, I said that b should be between 0 and 1, because if b more than 1, you need to subtract this integer 1, so it can be 0. So a can be anything. And if you want to find fixed points, you find fixed points x equals to ax plus b. And it will be only one of fixed points is indeed b over 1 minus a. But it's not the only one. It could be more if a is more than 1. Because if a is more than 1, we can have something like this, for example. So if b is non-zero, anyway, so we have this, for example, and this is not b over 1 minus a, it is something else, and this should be found. So what I suggested in lecture notes, I suggested to consider fixed points, all fixed points, there could be many of them, and i's fixed point is b plus I over 1 minus a. So provided that xi is in this range. Then if I is 0, it will be on, for example, on this branch. But anyway, so this change in I means getting from one to another in these branches. And next point. So what if so a equal to 1, we already considered a equal to 1 if b is non-zero, where I didn't consider. Okay, let's consider it again. Xn plus 1 equals to Axn and plus b. If b equals to 0, we already considered, but if b is non-zero, then it will be some, for example, this is b. Then it will be something like this. And this now, this we can, well, there can be fixed points, or there may be fixed points, may not. So this is also, it will depend on whether b plus I over 1 minus a, so between 0 and 1 for any a, for any integer I, sorry, for any integer I. So this is the question. If there are such, then we will have fixed points, otherwise we will not have fixed points. So if a is 1, if A is 1, okay, here, for example, it is quite good. A is 1. Here, slope 1. Here, slope 1. No fixed points. If A equals to 1, we will have denominator infinite, and we can't use this formula. That's it. And so next interesting question is about being rational and irrational numbers. So we considered this guy rational and irrational, but we didn't consider this guy rational or irrational. Xn plus 1 equals to I think it doesn't make big difference. So this AX in let's put it like this. If A is rational and say A is more than 1, if A is less than 1, we have convergence to 0. So it's not interesting. And if A is more than 1, then we will have chaos if X naught is irrational. I think I have we seen it when A was equal to 2. When A was equal to 2, we've seen it on Dublin map, but it would be for any rational A, in fact. We have chaos if X naught is irrational. But if A is irrational itself, then this is not quite correct, because I will give you example. Example like this. Xn plus 1 equals, let's say, square root of 2 times xn. X naught equals to say 1, or let's say half, which is rational, but your solution will be chaotic anyway, because this is irrational. Yeah. So if A is rational, then for rational X, we have periodic solutions, or yeah, let's say periodic. And if, what is it? And if this is irrational, then we can have chaotic solutions even when X naught is rational. So this is what I wanted to say, but I said it a bit awkward way. So this is my comments on problems 1 to 3. Now, problem number 4. Problem number 4. Okay, maybe. So this problem was done in lecture number 14, I think. This, in a sense, it's relatively easy starting point, because what we have here, xn plus 1 equals to, let's say, axn 1 minus xn. It is, we know this very well. It is logistic map. And for logistic map, we know that we have two fixed points, x1 equals to 0, x2 equals to what it was, 1 minus 1 over a. And we know when they are stable. So x1 is stable if a is between 0 and 1. Well, we don't need to include 1. And x2 is stable if a is between 1 and 3. That's what we remember. So if you are not sure, if you don't remember this, go back to lectures. This is something you're supposed to remember, maybe at least till exam, maybe even longer. But this was fine, and we had even two periodic solutions. Yeah, two periodic. I don't remember X3, X4. X3, 4. I don't remember what it was. You can find it. But what was they were stable. If A is between 3 and I don't remember what it was, 1 plus square root of 6, I think. I don't remember. I think square root of 6. Or square root of 5. Who remembers? Let me find it. Yeah, square root of 6. So this is, again, so this is good to remember when you start this problem. But in this problem, we have still logistic map. But in logistic map, so here, what we were considering X is real number. Let's say X naught is real number between 0 and 1. And A was also real number from 0 to 4. Let's put it like this. But in new problem, xn plus 1 equals to A xn 1 minus xn. Now, x naught is any complex number. So x naught belongs to C. And A is also, let's put it like this, any complex number. So this is what we do. And this in this complex plane, we have kind of new problems, new kind of problem, which is not set for real maps. So this is a complex plane. Let's put it like this. So now xn is how what ideally I would use different notations. Let me use different notations. So for this now, I will use Z. Z is good for complex number. So now I will say Z is, let's say, Zn is xn plus I yn. It is common notations for complex. And A would be an plus ibn, for example. I don't remember what I did in lecture notes. In lecture notes, I used C. Okay, I will keep it like here. And now here at one hand, we still have the same question, like find fixed points and their stability. And I think this problem is about finding fixed points and finding two periodic solutions and analyzing their stability. This is what is asked in problem number 4. But this is related to Mandelbrot sets, and in Mandelbrot sets, there is another problem. So let's put it like this: for given A and given Z naught, we can calculate this solution. Yeah, for given A and given Z naught. Let's clean it. Let's say A and Z naught are given. Then we will have solution Z naught, Z1, so on, Zn, and so on. Now let's consider absolute value of Zn, which is square root of xn squared plus yn squared. Yeah, it is modulus of complex number. And the question here, whether it tends to infinity or not. If it tends to infinity, it's not interesting, it's unbounded. So the question is whether we have bounded. Do we have bounded solutions? In fact, are they bounded or not depend on A and Z naught. This depends on A and parameter A and initial value Z naught. So it is still quite big problem and confusing. So this is simplified or just made it more specific. So specific is like this. If whether for given A we have bounded solutions. So what it means, where A is given, we can pick up any Z naught and check solution is bounded or not. If we don't have any bounded solution, then this A is not very good. Then nothing interesting. But if for given A we have such Z naughts that our solution is, then for which solutions are bounded, then these A's are good. This set of values of A are good. And this set of values of A, they are called Mandelbrot set. Set of values of parameter A for which we can find Z naught such that the orbit means solution is bounded. So this is general problem, the most general problem for maps on complex plane. And this was, I addressed again, so there are some courses which are completely devoted to Mandelbrot sets, but in my course I got only one lecture on this. Usually I try to avoid it on exam, these kind of problems. Well, I don't know what I will do this year. Probably I will skip it also. But at least you have it in your problem sheet number 3. You have, no, I'm not asking about a Mandelbrot set, but at least you deal with map on complex plane. Yeah. And now we can get back to our problem here. So in our problem, so we want to find fixed points for this zn plus 1 equals to 8zn times 1 minus zn. And this will be eventually same. So again, so fixed point is solution of z equals to 8z 1 minus z. So again, z is 0 is one solution, and second solution is 1 equals to 8 times 1 minus z. Now the problem here is that, so we have this z, which is 1 minus 1 over a, but this is complex number. Since a is complex, z is also complex. If a would be real, then we would have what we had in our logistic map. But if a is complex, then generally this is not necessary. It could be it is in fact, could be located anywhere on complex plane. So this is first part of story, and second about stability. Stability is again, so all rules are the same. For stability, you require for derivative to be, sorry, not equal. To be less than 1. Yeah, there is some difference here. Difference is this: if when derivative of real number of real function was a real function, and then we can say this is indeed less than 1. But f prime of z is complex number. So this is generally I would have to show it more carefully, but I think I escaped it everywhere in lecture notes and also in the video. I don't remember what was there. So this should be modulus of complex number. So what it means? It means that square root of real part of f prime squared plus imaginary part of f prime squared. So this guy should be less than 1. So it will be always positive, but it should be less than 1 for stability. And now we can get back to our map. So derivative of our function was a minus 2az. Derivative at 0 is a. So this is stable if modulus of a is less than 1, or real part of a squared plus imaginary part of a squared less than 1. So this is condition for z equal to 0 to be stable. And second is, so z, it was z1, yeah. z2, second fixed point, which was 1 minus 1 over a. So we have a minus 2a times 1 minus 1 over a. And what it was, I think it should look like how it was looking like before. A minus 2a plus 2 minus a. And now so this 2 minus a by absolute value should be less than 1. And this is a plane 2. So I will, this is, or maybe it's not pain. Eventually here it should be relatively easy. So look, so this is, well, at least this here you will need to think about. What kind of, what region on complex plane is this? With this is easy. This guy is easy. because if you have complex plane, A by absolute value less than 1 means circle. So radius 1. This is I minus 1 minus I. Yeah. So this is if A is any point in this circle, then modulus of A is less than 1, and therefore fixed point 0 is stable. And I don't want to plot it. This I will leave it to you to plot it. It's a bit, so at least idea is here on simple, and here I would ask you to work this. And now if we get back, so this is about so at one hand, if again, if A is inside of this region, we have stable fixed point, and therefore we have bounded solutions. Therefore, this should be part of Mandelbrot set. And this is, by the way, another part. If A is there, we have bounded solutions. We have solutions which converge to 0, bounded. If A satisfies this condition, then we have second fixed point is, which one was second? This one is stable, and therefore there are solutions which converge to here, and therefore they are bounded. Therefore, if this is satisfied, we are inside of Mandelbrot set. If this is satisfied, inside of Mandelbrot set. And idea here is like this. You find, for example, two periodic solutions. You find conditions on A for two periodic solutions to be stable. And these conditions are give you extra regions which are also belong to Mandelbrot set. And then you will find other, for example, 4 periodic solutions when they are stable, 8 periodic solutions. And so every time when you find values of A which satisfy conditionality of any periodic solutions, this will be extra regions on complex plane which belong to Mandelbrot set. And this Mandelbrot set, well, I would maybe use, at least in this video, which in one of this video, I have shown another video from the web about Mandelbrot sets. It's very spectacular. So you can try, just say Mandelbrot set YouTube, for example, and watch any video you will get there. They're very attractive. This is, so why there is something which I don't remember if I told in the lecture. So main point why Mandelbrot sets were introduced before fractals. Mandelbrot sets themselves are fractals. And this is also seen from, if you just find in YouTube any video which just illustrates the structure of Mandelbrot set, you will see that Mandelbrot set contains, if you zoom inside, look closer and closer, you will find pieces which resemble its all, like in this scale, like 1 scale, size of 1, 2, you see some pattern. Then if you zoom it like 1,000 times smaller, you will find exactly same structure. And in this structure, you can find point where you will zoom again like 1,000 times, and you will eventually see exactly same structure. And this getting inside and inside can continue infinitely. So this is why it's called fractal structure. Okay. So this, maybe I will stop here about these maps on complex plane. So I don't want to completely show this. Stable 2 cycles, it is again. So this is, you will have conditions for your parameter A, and just make some judgment of what kind of region it could be. Well, I mean, if you can't judge, just say, this is kind of region on complex plane. So this minimum what you can say. Maximum you can try to find out like this circle here. This eventually will be also a circle. So these two circles are easy. With stability of 2 cycles, it is more sophisticated. And I don't remember, I didn't look at solutions. I don't remember what it was there. Just go ahead and try it. Okay, questions? Okay, now problems 5, 6, and 7 is they are about finding, well, about fractals and fractal dimensions. Problem number 5. Contrast middle fifth is produced by the iteration process of dividing into 5 segments and removing the open middle fifth segment. So it's a relatively simple case. So this is problem number 5. You have a segment of length 1, it's what you start. Then, so this is step note. Then at step 1, I will put here step 1. You divide it into 5 pieces. You divide it into 5 pieces. 1, 2, 3. This is 3, this is 4, this is 5, let's say. So this is 1, 2, 3, 4, 5. So what happens? You remove this one piece. So at step 2, what you do at step 2, so some students understand this. It's interesting that every year at least 1, sometimes 2 students do it different way compared to how I read these conditions. So now you divide, so this was your first segment. You divide it also on 5 pieces and remove middle one. So this was first one. Then do the same with second segment. So then you have only 4 segments. You do with 4th segment. So this is on step 2. Yeah, let's consider now how it. So first problem is find length of remaining intervals. Okay, let's find length. L naught is 1. L2 is, you see, we have 4 segments, and length of each segment is 1 over 5. It's 4 over 5. It's L1, sorry. L2 would be, now each of these 4 divided into 4 pieces, therefore it will be 4 squared segments, and size of length of each segment, it's again 5 times smaller compared to step 1. It will be 1 over 5 squared. So this is 4 over 5 squared. And you can conclude that Ln is 4 over 5 to the power of n. And from here you can find limit of Ln when n tends to infinity. So this is easy. To find fractal dimension, you count number of segments and length of segments. Length of segments, you will take a scaling factor, epsilon. It's like size of your box. What it means. So you, to cover your original segment, you need a ruler of size 1, and you apply it only once. you have only one segment of length 1. So length 1. So here on step 1, you will need to apply your ruler 4 times and size of your ruler 1/5. On step 2, you will need 16 rulers and size of ruler 1/25 and so on. So this way you find what happens on step n. It's more or less step n. You will find it, and then you will use your formula for box counting dimension, or for capacity. Sometimes it's called capacity dimension. So this was limit when n tends to infinity of logarithm of n divided by logarithm of 1/epsilon. So why? So in fact, so formal definition is this, but if you do calculations correctly, if you use these rulers correctly, at least you find sizes of rulers correctly, you eventually will find that this ratio of these two logarithms is always the same. It's the same on first step, on second step, and so on. So it's not changing. And therefore, you can just take this ratio on step n, step 2, it's whatever, and it will be same answer. So what probably I forgot to tell you in my video is about being careful about scale, about self-similarity. Yeah, so first what I wanted to tell is about self-similarity. So if you consider this segment here, you have 4 segments here, and each of these segments is similar to this one, to original. This is one similarity. If you take here, for example, this segment, and stretch it 5 times, you will see that it will be exactly this. You stretch it, you get this. So this is why it's called epsilon is self-similarity scale. So it is important. So you have your epsilon size of your ruler, it should get down. But it is important to get down not arbitrary, but according to self-similarity scale of your fractal structure. It is not only making easy, it is sometimes you avoid problems, because there are some cases when if you don't follow self-similarity scale, you can end up with wrong dimension. This is one danger which is there about self-similarity. And second danger is that eventually not all fractals have definite self-similarity scale. So there are some strange fractals which they indeed have subpieces, and the subpieces are similar to larger pieces or to original piece. But these subpieces can be of different size. So this means that this self-similarity scale is not properly defined. This can be seen in some vegetables like brussels probably, or so you can imagine. I don't remember if I can, well, if I will find some images for this. Leaves. Good example is leaves. So there are leaves where you can look at leaf and you see that it contains parts which are similar to original leaf, but these parts not of the same size. For example, one leaf can contain like 8 smaller pieces, but these pieces from base to top getting smaller and smaller. But then so each of these pieces is equivalent to or similar to original leaf, but scale of self-similarity will be different for these different parts. And this makes it difficult, for example, in case of leaf, to calculate, or to use this procedure for calculating fractal dimension. And in fact, it's again, there are courses on fractals and fractal patterns, and on these courses, people introduce, syllabus includes many different definitions of fractal dimensions. So in our course, I just introduced one, which is called capacity dimension or box counting dimension. This is simple, and in simple cases, it works perfectly well. And you will see only simple cases. Okay, so this is about problem number 5. But problem number 6 is pretty much the same. The only extra piece is what I didn't deliver, what is on page 11 of lecture notes, 2. So I will show you how to sketch this F and what it means, this set S of initial points. Anyway, I will do one more lecture on fractal patterns, and there I will talk about this also anyway. So what we have some map defined by this F. What I can say, I will put it like this. It is pretty much the same. This is 5x mod 1 if x is between 0 and 1/5, x is between 2/5 and 3/5, and x is between 4/5 and 1. So this is first condition. And second is 0. Well, we can keep it otherwise. So slope is 5. So no, my mistake. Between 1/5 and 2/5, we don't have anything. So we have here. So this is your function. So this is one. And now, so you can do, if you do second iterate, each of them will be multiplied by 5 again. And therefore, this will get, for example, to 1 when x n plus 1 equals to 1 over 25 now, because slope will be 25. If slope for this is 5, slope for double map will be 5 squared. Slope for triple map will be 5 cubed, and so on. So this way you produce your map, so iterative maps. But what is important here, so what you want to pay attention on, so here are xn plus 1, let's say x1 is non-zero if x naught is here, or here, yeah, belongs to one of these 3. But then x2 is non-zero if x1, and then you will find out that this will be smaller segments, and these sizes of these segments will be 5 times smaller than sizes of these segments, and number of them you will be supposed to count. And this will be, it will be very similar to what we did before with Cantor's middle. So this is, you can consider this as Cantor set. You have this, and this. So you had segment of length 1, but what we did now, we divided into 5 pieces and removed this piece and this piece. So what we got on step 1, we got 3 pieces of length 1 over 5. Then on second step, you will have 9 pieces of size 1/25 and so on. Yeah. So it is another way to represent counter set. It's that version of counter set. And everything will be the same. So as soon as you can see, so this is for F. Then for F, second iterate will be, I don't remember, something like this. So it will be F2 and so on. And so after you understand this, everything gets back to problem number 5. Okay. So I will consider that we discussed problems 5 and 6. Problem number 7, it's slightly more complicated, because so now you have, it's about fractal. So you have a chessboard, in fact. Yeah. I will plot it like 2 by 2, but in fact it should be 8 by 8. So what happens here? So you have, for example, this black part, black field, or black cell, and white. So like in chessboard. Then, so blacks, for example, you get removed blacks, and whites you divide also into pieces and remove. So 2 of them will be black, 2 of them will be white. You remove black, and this way, step after step, you will get fractal pattern. It is more similar to Sharpinsky triangle. If you look at Sharpinsky triangle, you will see that it's very similar way. It is different geometry, but idea is the same. And here also you will need to calculate number of boxes every time and size of the box every step, every iteration, and then you will use definition of capacity dimension to calculate this dimension of this fractal. Good. So questions. I will stop sharing. Okay. Okay, do you have any questions? Okay. So just ask me something. If you're not asking anything, then we can stop now. So I stop recording.